Hello, everyone. I would like to thank the organizer to have this video conference. And today I want to discuss gravitational wave memory effects and the bounding imaginary symmetries in skeletal theories. This talk is based on the two works here. There are 5 sections in my talk. Firstly, we know that the gravitational wave memory effect refers to the permanent change in relative distance between test particles after the passage of gravitational waves. From our everyday experience, we know that after the water wave recedes, water level returns to its original position. This may not happen to phenomena involving gravitational waves. So how to understand that? In GR, it turns out it has something to do with symmetries living on the non-infinity, represented by this line in this diagram. Of course, if a spacetime has horizon h, then there also exists a non-infinity here. Non-infinity, roughly speaking, is a place very far away from the source. So gravity there is very weak, and the spacetime is basically flat. So they expect that the symmetry on non-infinity is just the Poincare symmetry. However, it turns out the symmetry living on non-infinity is larger than Poincare symmetry. It includes Poincare symmetry, but also includes simple translations. Those are generalizations of translations. Because of the simple translations, the vacuum states on the non-infinity are degenerate, and they are related to each other via the simple translations. That actually explains the presence of a gravitational wave memory effect in general relativity. Of course, there are many different modified gravities, and such as scalar tensor theory, Einstein ether theory, teleparallel gravity, and so on. We would like to study memory effects in those modified gravities, and as a first step, we want to study the simplest one, Brans-Dicke theory, whose action is given by the following expression in Jordan frame. The scalar field phi is coupled to metric non-minimally. Of course, you can perform a conformal transformation, and in the Einstein frame, the scalar field phi tilde is basically a canonical scalar field. Anyway, we want to study memory effect and their relations to asymptotic symmetries. For that purpose, we want to just solve this set of equations to find the solution describing the asymptotically flat spacetimes. For that purpose, you want to use the generalized boundary Sachs coordinates. U is time, basically the retarded time at non-infinity. R a radius, theta and phi are angular coordinates. In these coordinates, the metric is given by this matrix. It has several vanishing components. Its GR component is 0, so radius R is basically a null direction, which is basically the gravitational wave direction at non-infinity. Later, we will also require that this part of the metric should have the following determinant. We also want the boundary conditions to be satisfied. Those boundary conditions just guarantee that the spacetime near non-infinity look like they are flat spacetime. In particular, HAB is given by R squared multiplied by gamma AB at the leading order. Gamma AB is simply the round-2 metric on the 2-sphere. It's still very difficult to look for the exact solutions, so we just want to write down some expansion solutions. Here we expand phi and HAB, find out its constant, phi1, phi2, c hat AB and d hat AB are functions of time and angular coordinates. C hat AB and d hat AB are also traceless. We finally want to expand the matter energy momentum tensor TAB but their expressions are so complicated, so we don't want to present them here. Then you just go ahead to solve the equation of motion, and you will find the components of an autometric. For example, GUU is given by -1 plus this term. This M is called the mass aspect, and it's related to the total energy of the system. UR component is given by this expression. This is for the UE component. There's a new function NA, which is called the angular momentum aspect. It is related to the total angular momentum of the whole system. We also obtained the evolutions for the mass aspect and angular momentum aspect. In those expressions, there are two new quantities. This is called the New's tensor, which is basically negative time derivative of c hat b. This is n time derivative of phi 1. It turns out when there are gravitational waves, at least one of them should be non-vanishing. But when there are no gravitational wave, both of them should be zero. This means that c hat ab and phi 1 are relative degrees freedom because they represent the gravitational waves at non-infinity. At last, we just want to discuss a little bit about the gravitational wave polarizations and their relations with the memories. We know that interferometers measure the gravitational wave using the geodesic deviation. This equation describes the relative velocity acceleration between test particles. Capital T is the velocity of the test particle. S is the deviation vector, basically the relative distance. Using the previous solutions, we can rewrite this expression to find out that the second time derivative of S is related to the electric component of the Riemann tensor. At the leading order, this tensor is just related to the second time derivatives of those relative degrees freedom. To understand the memory effect a little bit, we can integrate this equation twice to find the change in S. If, for example, in the end, there's no gravitational wave, and the delta S is non-vanishing, we see there is gravitational wave memory effect. By looking at this equation, we find out that at the leading order, there are two contributions to the memory effect. One is from the tensor gravitational wave, the other is from the scalar gravitational wave. So in the future, we will discuss the memory effects in both the tensor and scalar sectors. Before that, I want to know something about the asymptotic symmetries. Those are basically the diffeomorphisms that preserve the boundary conditions. It's difficult to look for the finite transformations, but we can study the infinitesimal version of that. That is represented by a vector field C. Its actions on the metric and the scalar field are given by those expressions. By studying them, one find out that C is described by two different functions. One is alpha, which defined only on the two sphere. The other is this vector YA, which is also function defined on the two sphere. It turns out because of the two sets of functions, there are two sets of basic transformations. The one though with alpha are called super translations. In particular, if alpha is given by the linear combination of L equal to 0 and 1 spherical harmonics, it describes a translation. A generic super translation is just a arbitrary linear combination of all of those spherical harmonics. The other set of transformations are parametrized by capital YA, which is conformal vector field for gamma AB. So it generates Lorentz transformation, and therefore the asymptotic symmetries include the simple translations and the Lorentz transformations, and of course their combinations. We want to know how those transformations act on those relative degrees freedom. Their infinitesimal versions are given here. Those are not so illuminating that we want to consider some simple situation. Let's assume there is no gravitational wave. So both n and NAB should vanish. It turns out that simple translation doesn't transform phi1, but it transforms C hat AB. A Lorentz transformation transforms all the relative degrees freedom given by those two expressions. Those are very useful to understand memory effects. More precisely, memory effect is a lasting change in relative distance between vacuum states at non-infinity. So we want to know what the vacuum states are. In scalar factor, a vacuum state is just the state described by a time-independent phi1, but in tensor factor, it's a little bit more complicated. You should not only require the time independency of C hat AB, but also require that C satisfies this set of equations. By solving this equation, one found out that C hat AB is given by a single function, capital C, defined on the two sphere. Now imagine, in the beginning, there is a vacuum state described by this C hat AB. And then we perform this simple translation. We would end up with C hat prime. This one is also determined by a function C prime. C prime is basically C minus 2 alpha. This means that this also represents a vacuum state. It is a different vacuum state from the original one. Because of this difference, memory effect exists in tensor factor. This effect is constrained by the evolution equation of the mass aspect given by this equation. Here, these three terms actually are the energy fluxes penetrating the non-infinity. We can similarly explain memory effect in scalar factor. We know that simple translation doesn't change phi1, but a Lorentz transformation changes it. So there are also multiple vacuum states in scalar factor, and those states are related to each other via the Lorentz transformation. Those memory effects are constrained by the evolution equation of the angular momentum aspect. This expression is pretty complicated, but notice that the last three terms are basically the angular momentum fluxes penetrating the non-infinity. That's the end. We summarize. We studied the metric of an isolated system in Bryan-Sticky theory in the generalized boundary Sachs coordinates. We then identified the asymptotic symmetries and their actions. We found out that memory effect in tensor factor is related to simple translations that transforms one vacuum state to a different one. Memory effect in scalar factor is because of the Lorentz transformations. In the future, we would like to investigate memory effects and asymptotic symmetries in vector tensor theory, scalar tensor theory, etc. Notice that in those theories, there are more degrees freedoms, and some of them may even violate local Lorentz invariants. So there could be many new phenomena. We hope by studying memory effects, we could find a new way to probe the nature of gravity. So this is what I just want to share. Thank you very much for your attention.